Hello everyone. So here I want to show a simple technique which was used to improve lower bound can be turned into algorithms. It's basically shrinkage under random restriction approach. So let's first review this technique which was used to prove formular lower bounds. So here I'm considering De Morgan formulas. It's just a binary tree where the internal nodes are AND and OR gates, the leaves are literals. So for the random restriction, I want to do it step by step. So you repeatedly pick a variable randomly and randomly fix it to be either 0 or 1. So using this approach, so if you think of each individual leaf, by randomly fixing the leaf, you can eliminate 1.5 leaves on average. And then given this formula of size S on n variables, if you pick a variable randomly and fix it, in expectation, you can reduce the size by this 1.5 times the average frequency S over n. So this is upper bounded by this. So if I do this step by step until there are Pn variables left unfixed, the size is going to shrink by a factor of p to 1.5. So this 1.5 is usually called the shrinkage exponent for the De Morgan formula size. Okay. And this 1.5 is actually not optimal. It was shown by Hastad that this shrinkage exponent can be improved to be almost 2. And this 2 is actually optimal. So you can construct a De Morgan formula of quadratic size that compute parity exactly. So that means the shrinkage exponent cannot be improved above 2. Okay. So this shrinkage under random restrictions was invented to prove formula size lower bound. That directly gives that parity requires. So if you can show some model, circular model that has shrinkage exponent gamma, that directly implies parity requires size n to gamma. And Hastad, and Jiu actually constructed a simple function which also doesn't have good shrinkage. It requires size n to gamma plus 1 minus little 1. And by Hastad's result, this gives the formula size lower bound almost n to power 3. So that's the best known formula size lower bound we have now. Okay. So recently, this shrinkage approach was strengthened to concentrated shrinkage. So previously, we say the shrinkage of formula size in expectation. Here, we can strengthen it to be shrinkage with high probability. So here, I'm considering a different family of restrictions. Let's call it greedy restrictions, where it's simple. At each step, you just pick the most frequent variable appearing in the formula and randomly fix it. So it can be proved that if you do this after n minus pn steps, then with probability exponentially close to 1, the formula size is going to be upper bounded by 2 times. It's like the expected size. Okay. This can be proved using Azuma's inequality for super martingales. So this approach can be viewed as an algorithm where you do this branching level by level. At each level, you pick the most frequent variable and build 2 branches by fixing the variable to be 0 in one branch, 1 in the other branch. Okay. Now this shrinkage property can be turned into satisfiability algorithms. So let's suppose we start with a formula of size Cn on n variables. And I can choose this p to be 1 over some constant times c squared. So by the previous shrinkage property, I can argue that I do this greedy restriction for n minus pn levels. I can argue that most of those branches will have formula size at most half of pn. So for all the branches, I will have pn variables left unrestricted. But for most of the branches, the formula size are very small, half of pn. Okay. So that means for a satisfiability algorithm, for the branches with small formulas, you just do brute force search on those variables that are left on the small formulas. And then for the tiny fraction where the formula size does not shrink well, you can also do brute force search on the remaining variable. Okay. So after I build up this branching tree, I can just count the number of satisfying assignments on the leaves of this branching tree. That gives a sharp set algorithm. And the total running time is going to be bounded by this amount. So this algorithm is not trivial for C to be, let's say, less than square root of n. But using memoization technique, I can somehow improve the algorithm for larger size. So suppose we start with formulas of size n to 2.49. In this case, I can choose p to be a very small fraction. So I want to restrict all but n to 0.001 variables. So I restrict all but such small number of variables. And we can argue that most branches after n minus pn levels of restrictions will have formulas of sublinear size. And then I can just build up a lookup table to enumerate all possible formulas of such size and use that lookup table to speed up satisfiability checking at the bottom levels. So that gives improved running time like this, but for size larger than this CN. Okay. Now, since we know that the shrinkage exponent for De Morgan formulas is 2, so this size, so the same algorithm can be somehow generalized for a larger size. So essentially, in a recent work by Tao, they give an algorithm that runs in same time, but for size n to 2.99. It's like n to gamma plus 1 minus some little constant. So this matches with the best known formula size lower bound we have. Okay. So let's step back and look at this algorithm. It's actually very simple. So it's like DPL style branching algorithm, except that memorization part. Okay. So at the high level, so we start with an instance of size s, and then I want to do graded restriction to shrink the instance size by this factor p to gamma. So I just need this to happen with high probability. And at the end, I will have very small shrinked instance. So depending on the parameters of s and p, I can either use some known algorithm to solve these small instances, or I can use memorization. Okay. So, but for the small fraction where the shrinkage does not happen, I can use brute force search. So it's simple. Let's call it a template of algorithms. Now let's see how I can use such a template to solve some other problems. Okay, before that, so when I see this size s, it can actually be generalized to be a weight function or general measure. So people have tried to use this measure of weight function in order to improve the shrinkage exponent. And if we can improve the shrinkage exponent, it implies better algorithm. Okay. So now let's see how to use the same algorithm to solve Sparse MAX-SAT. So in this setting, we are given a CNF, but with Cn number of clauses. I want to find an assignment that satisfies a maximum number of clauses. So here, I want to put a measure on this instance. The measure is actually like trivial. So you just put measure 0 on one clauses, measure 1 on two clauses, and measure 2 on all other clauses, no matter how long your clause is. And then using graded restriction, it can be argued that you can have shrinkage exponent 2 for this kind of measure. Oh, sorry, I forgot to mention. So the measure on the whole instance is just the summation with the measure on each individual clause. And then after this shrinkage, well, you can choose a specific p to be in the order 1 over c. And you can argue that after I do this n minus pn graded restriction for n minus pn steps, most of the branches are going to end up with almost all of the clauses are 1 clauses. So you might have some very few number of long clauses, but there are very few, so you can do it naively to eliminate long clauses. Okay. And then for these small clauses, you can solve MAX-SAT in polynomial time. For the small fraction where shrinkage does not happen, you do brute force search. Okay. This gives this running time like this. So this algorithm was first used by Saki, Seto, and Tamaki. Over there, they were using the measure as the size of the given instance, like the number of literals appearing in the instance. So in this work, they were using somehow like a larger measure, but use a shrinkage exponent 1.5. So in this work, we somehow make this measure more trivial, and then improve the shrinkage exponent to be something larger, and then improve the running time. Yes?
So could you So why? I mean, it is clear why you put the weight 0 to 1 clauses, but
yeah, the intuition is if you have longer clauses, then if you do random restriction, you have better chance to kill that clause completely, because there are lots of variables appearing in that long clause.
But basically, we don't know for widths bigger than 2. We can't really distinguish between them in terms of solving them better. So it's only with yeah.
So do you mean that part of the reason is that we know how to solve max-2-SAT faster than?
Yeah, that's the next slide. So this one is essentially a reduction from max-SAT to max-1-SAT. But since we know there exists efficient algorithm for max-2-SAT, so you can somehow build this branching by reducing max-SAT to max-2-SAT and apply Williams' algorithm for max-2-SAT at the bottom levels. So here, somehow you can slightly change the measures. Basically, the intuition is you put 0 measure on all 1 clauses and 2 clauses, and non-zero measure on others. Okay. So using this measure, you can improve shrinkage exponent to 3, and then improves P and also the running time. But this algorithm requires exponential space because it was required by Williams' algorithm for max-2-SAT. Can this still be improved? In a recent work by Saki, Seto, Tamaki, and Terurama, they give an algorithm that can solve max-SAT on polynomial number of clauses. So here the idea is also simple. So basically, at a high level, not very precise, but at a high level, you put 0 measure on clauses on at most less than k variables, and non-zero measure on clauses of length larger than k. And then using that, you can, by greedy restriction, you can get shrinkage exponent to be almost a k over 2. And this k is at your choice. You can choose any k you want. Okay, so for the algorithm, I can choose k to be 4 times s, and then choose p to be something very small, like n to the power of 1 over s divided by n. So using such parameters, you can essentially, you build this greedy restriction tree. You can reduce max-SAT to max-k-SAT. So basically, at the bottom level, for most of the branches, all clauses of length larger than k are going to be killed by this greedy restriction. And then you can use memoization for max-k-SAT at the bottom level. So that gives the running time like this. Okay. So the good thing here might be for all the previous examples, we have very small shrinkage exponent, like 2 or 3. But here, you can really choose a parameter k as your shrinkage exponent, which might give you better shrinkage. And it might allow you to solve instances with larger size. Now, the same algorithm can be used to replace one step in this satisfiability algorithm for Sparse Depth-2 TC circuit by this Impagliazzo-Paduri-Schneider paper recently. So here, I want to reduce Depth-2 threshold circuit with linear number of wires all the way down to Depth-2 threshold circuits with very few number of gates. So it's also greedy restriction. You can define measures, but this measure is actually very trivial. It's the number of wires between the inputs and the level 1 threshold gates minus the number of gates. And then you can, by greedy restriction, you can show a shrinkage exponent which is slightly larger than 1. And that will help you reduce the case from linear number of wires to TC0 with very few gates. And then the heart of this IPS approach was actually an algorithm solving this base case problem. Okay. So in IPS paper, it was proved using different way, but using this shrinkage approach, we can somehow give a simpler proof of their result. So at a higher level, if you want to apply this algorithmic template, there might be these 3 things you want to specify. You want to define a measure on the instance, and you want to show a better shrinkage exponent under certain families of restrictions. And then you want to have some base case algorithms solving the reduced instance. So although when you define this measure, you might have the base case at mind. So basically, for base case instances, you want to put measure 0. And then you want to give one measure such that you can have the best shrinkage exponent. So I've shown some examples, but the same approach can be applied to other cases like formulas over 4 binary bases, max-SAT, and also even sparse polynomials. So the intuition is that this greedy restriction approach somehow gives you a way to reduce short instances to instances with small widths. If you think of CNF, it gives you a way to reduce CNF to KCNF. There are some other uses of concentrated shrinkage. It can be combined with other techniques to get average case lower bound and also pseudo-random generators. So that's all what I want to say. Thank you very much.
Any questions? Okay, thanks, sir.